Okay, so
Don't get too ahead of yourself.
So we've done translations and we looked at moving it left 3 up 2. So for instance, if I was going to represent it, say this shape, but we haven't actually got a shape. Maybe I can, let's put some stuff on. If I had just a triangle like this, what does it look like to translate that shape left 3 and up 2?
You pick a point.
Pick a point.
Yeah, true.
And we move 1, 2, 3 left and 1, 2. Okay, so if that was point A, this would be point A.
Yep. And then
Dash.
Okay. Dash.
Remember that?
Yeah.
And then my new shape would end up being here. So that was a translation. Okay.
Yeah, that's easy.
Right. Now, here's where it's all linked, you see. So what I could do is actually say that from this point here to this point, it moves like that, yeah? Mm-hmm. Now that arrow is a vector. That's basically what we're doing. Now we have to represent that slightly differently than saying left and up. So what we would say, it has been translated, and how do we represent that left 3 up 2, but in a better, more mathematical way?
Negative.
Sort of rise over run, or that's the other way around.
Or 3 over 2?
So it's
2 over 3 over 2. Right over rise.
so 3 over 2,
With
but
a little arrow.
no.
That big.
What's wrong? What's negative?
The 3.
3.
Because you're moving that way.
This is negative. It's right.
So do you remember we had, if we think about if a vector goes up
Oh, it is.
or it goes to the right, then we have positive values, just like a set of axes.
I get it.
But if we go a different direction,
It links.
if we go this way or this way, we are going in negative directions. So left and down is negative, up and right is positive, just like a set of axes. Right? Now, I'll give you a chance to write that.
I guess it's a
Right, so this is the direction component of a vector. So depending on what those numbers are, that's the direction. Now, just based on what we talked about, what do you notice about our across 3, up 2, and then a line joining those 2 points? It's a right angled triangle, thank you. So eventually, what do you think you're going to have to do within a vector?
Pythagoras and trigonometry.
Well, is there going to be trigonometry necessary?
Well, not
There could be if you had to find the hypotenuse.
Well, that I would say would be Pythagoras.
If you had to find the angle of it.
But if we were to being asked to find an angle of a vector, then yeah, we could do trigonometry. Would we be able to find the angle?
I mean, like, I guess you could.
We could, yeah, because I've got the -3 and the 2. I know we've got a 90-degree angle. What ratio would I be using if I know the left, right, up, down? Which one would I use out of SOHCAHTOA? TOA, yeah? Opposite, adjacent. If I was asked to find the angle of within that. See, can you see how this topic again is linked? Right, so Pythagoras theorem, trigonometry. Are you ever going to have to do sine rule?
No. No.
Probably not, but could you be asked to do
Yeah. Maybe.
I'll re-ask that when the questions get a bit more sort of compound question, not necessarily. You're probably not going to get it, but when we have to do more than one thing at once. So what we've got here is a direction. If you think about this, what I said just up here was magnitude and direction. So what do you think the magnitude thing could represent? Do you know what magnitude means?
Big.
So magnitude, I'm sure you've heard of the word magnitude in geography, probably.
No.
Measurement. Well, actually, the word magnitude is not.
Size.
It's to do with size, isn't it?
Yep.
It's not specific to earthquakes. Magnitude is just how large something is. So if we said we have magnitude as well, how do you think that relates to vectors?
How far?
Size change, how far the translation goes. So if I asked you for a vector that had a larger magnitude but the same direction as the one I've just done, what would you think?
Wouldn't that be an enlargement?
-6/4.
Okay.
Good job, yeah.
Oh.
So if I did
I was making the line slide.
-6/4,
It's
Okay.
still equivalent.
yeah, so I would then be looking at doing a line. So I've got to go -3, -6, and then I go up 4, and there is my vector, right? And it's twice as big, but exactly the same direction, yeah? Okay, so this is what we're talking magnitude and direction. We'll talk more about it, but that's what we mean, right? So what we're going to be looking at is how do you label them, how do we write a vector, how do we add and subtract vectors, how do you multiply by, I agree with you, a scalar quantity, right? I do, I agree with you. Say it properly, like it's meant to be. So multiplying by a scalar quantity. Do you know when I say things like scalar quantity or vector quantity, physicists amongst you, do you know any vector quantities?
Nope.
You're very quick at saying, no, I don't know something.
Is it a thermometer?
Can you, for
Yeah,
example,
yeah.
we use smaller vectors that we use in physics.
Temperature.
Do you know any vector quantities?
Vector.
So if we say a vector quantity has to have what?
A number.
Also, like gravity is like 10.
Magnitude and direction. So if anything's a vector quantity, it has to have. So, can you think from your physics?
Waves. Height.
Girl, I'll take physics.
The weight goes down and it's 10.
Okay, so gravity is a force, yeah,
Yep.
which is a vector quantity because gravity always acts
Dawn.
down towards the centre of the earth.
Something that has to have a speed and thing.
Can you think of
Speed.
again? Oh, okay. There's a speed.
Yeah,
So
but it depends which one.
Speed is scalar quantity.
Vectors have to do with, they are represented with arrows and have to do with direction.
Well, I'm asking, yeah.
Yeah, but velocity is.
So, right, well, hang on, let's sort that out because I think that's something that needs to be sorted. Scalar quantities have magnitude, but direction is not important. Okay?
Why not?
Vector quantities have magnitude and direction is important. So I say physics because physics is one of these where it's really obvious. So speed, maybe this will explain to you why speed has what you would say has two names. But speed and velocity are different because speed is a scalar quantity, right? But velocity is a vector quantity because speed is always positive, yeah? Velocity, however, can be negative.
Acceleration and deceleration.
Acceleration, again, my physics teacher told me there is no such thing as deceleration because there is. I argued with this as well, but I now accept what he was talking about. Acceleration being a vector quantity, a deceleration is actually an acceleration with a negative direction. Yeah? Velocity can be 10 meters per second in that way, but if I'm going that way at 10 meters per second, it's negative 10 meters per second. But speed would be 10 meters per second, doesn't matter which way you go. Okay? Right? Gravity, we've got that. Force against, your table applies a force in an upward direction against gravity. Yeah, buoyancy, all of these things are vector quantities. Okay? Alright? So let's get back to basics. Let's just talk what we can label them. So we've used them before, you know that. So let's just say this is a vector. If I said from point A to point B, I can say a couple of things. That AB with a line, that's one way of writing a vector. Another way to express it would be to say little a. Just call it A. Now I could have called it B, P, C, Q, whatever. But you notice how we either go point to point and we say A to B is, or we say vector A is, or we have it in our column form. Yeah? Does that make sense? And you kind of have to be able to deal with all of those. So for instance, if I told you that AB, okay, is minus 6, 4, we've looked at that, okay, and then I said A is also minus 6, 4, we've got the same vector. What would B A be?
4 over 6. 6 over 4?
6 over 9.
So what would it be? 6 over minus 4.
Oh, because you're going down.
I was going to get there.
Because what we're not doing is we're not just flipping numbers around, we've got to think what actually happened was the direction changed, yeah?
Right to the bottom.
So how would I represent that in terms of A?
A would be
So A is minus 6, 4, but
negative A.
negative A. So there's two ways of changing the direction of my vector. I can say, well, it's either, if it was A to B, it's now B to A. If it was A, it's now negative A. Okay. So when we do algebra with vector stuff, we'll be using this A and minus A and that kind of thing. But it just means negative, the opposite direction. All right? Does that make sense?
Yeah.
Okay.
Me too. I have to erase my
Okay, I want to go through.
Shoot.
Why do you do that? I've done it for once.
If you turn to page 486 in your book, let's have a look at an example question. Let's go through it together. Okay?
It hasn't even been
Okay, so we've got in this question A, B, C, D is a parallelogram, it says. Okay? So I'm just going to draw my parallelogram. Have I done it right? It's difficult to see from this angle.
You want them back. After you just go ahead.
Okay, come on. Right, so we are told that A to B is called A, and we are told that B to C is called B. So we've got these vectors in those two directions. Now, vectors have magnitude and direction. Now, you don't, at the moment, have to worry about starting points or anything like that. When you get to IB, if you're doing SL or HL, you'll have to talk about vector equations of lines, so you have certain points. So we're not going to that point. So vectors, in terms of A and B, that vector A has a direction and a magnitude, but it can be started and finished started at any point as long as it goes in that direction for that magnitude. Alright? So what we need to do, alright, is find out what B to A, how we would represent that. So at the moment, I've drawn it on squares, but we've got no grid, so we can't give it in component form. We can't give it as numbers at the moment, alright? But we can give it in terms of A and B. So B to A is just negative A, okay? Because it's just the opposite direction. Right? C to B is just negative B. Right. A to D. So A to D is something that is not labelled at the moment, okay? But A to D would be doing that.
Isn't that just B?
So that is just the same as doing B. The fact that it starts at a different place, but we know it's that because what shape is it? Parallelogram. So we know that A to D and B to C are the same length and they're parallel. So we can say that. And therefore, final one, C to D, negative A. Good. Right? Because we've gone the opposite direction.
Okay.
Okay?
From C, now I'm understanding. From C to B,
Pardon?
wouldn't C to B be positive?
Wouldn't B to A be
No,
positive?
because it's like parallel lines. So if A to B is going that way, D to C will be positive.
Wouldn't it be positive?
No, so I think, as Gisela said, A to B is going left to right, but C to D. Now what you're saying is that D to C is A. That would be the same. Okay?
Is that wrong or right?
What?
Nothing, never mind.
Everything written on the board is correct. So we were asked for C to D. So C to D is in that direction.
C to B.
If we did C to B,
Yeah.
it would be
Negative B.
negative B because it's in the opposite direction. So
Of the line.
But
okay.
also, it really doesn't matter what direction the arrows be.
no, it really does
does.
matter. It
So,
really
no,
matters.
Since you're going up,
Wait, what?
So, for
Only going
instance,
up now?
If I want to go C to B, I start at C and I go to B.
So you're going the opposite.
So I'm going in the opposite direction to what I'm told B to C is B.
So we're not worrying about the whole thing where it's like this thing.
Yeah, that's what we're talking
This?
about.
We're not worrying
No,
about
so
this.
like I said, there's no numbers at the moment because
So just-
there's no grid on that question.
Okay.
So what we're doing at the moment is we're just using geometrical features of certain shapes to help us do that. Okay? Right.
Yes.
Would you like to do one more together before I let you move on? Okay, well let's have a look at question 2 in exercise 24B. Okay, so we have, again, no grid. So I've got a line like that. I'm taking note of which way the arrows are going. Alright. And we are told I've got A, B, C, and I know that's Q, P, and R. Okay, so I've got to express what A to B is. A to B is? Go from A to B. So what it was quite nice is to have an arrow kind of halfway along so you can really see the directions. Okay. Alright, so A to B is P. Right. B to A.
Negative P.
Negative P. B to C.
Q. Okay.
Yeah. I guess they're going to ask C to B.
Negative Q.
Negative Q. Keeping it very basic. C to A,
R.
R,
Negative R.
and A to C. Okay. Now, let me just ask you a question. What do you think A to B plus B to C would look like?
A to B is P.
P to C.
It's P plus Q.
Okay, so we've got P plus Q. Alright?
Yep.
That is the same thing as what? But I want to simplify it. So if you think about it, I want to simplify it. So I am going from A to B, okay? Then I'm doing from B to C.
Ah.
But I could do that. This is where we move on to. That instead of doing A to B to C, I could just go
A, B,
do it shorter.
A, C.
A to C.
But that's not.
Negative R.
It's taking you to the same place.
Yeah.
So I go to the same place. So this is where vectors leads to. So it's actually the same thing as doing A to C, which is
Negative R.
negative R.
So it's the
Oh my God, so complicated.
This is called the resultant.
Is
Okay.
that triangle isosceles?
Don't know. There's no numbers.
No.
It's just lots of no. Well, we don't need to guess. I don't need to. That's not what I'm. There's no magnitudes being given. You know, it's just a set of directions at the moment.
Resultant force.
So the resultant is, yeah, it's basically the shortcut. Now for you, I've just heard a couple of you mention about the resultant force.
You mean just Leo?
Just okay.
For real.
That's because when we look at vector equation, when we look at vector quantities, a resultant force will make something happen. Okay. So, for instance, if a vector quantity like gravity applies on an object, if it's on a table, the force from the table is equal and opposite to gravity. Therefore, the object does nothing. All right? However, if the force pushing against gravity is less than the force of gravity, what happens? It goes down. Yeah? And what do you do when you jump then?
You go negative.
Well, you apply a force in an upwards direction that is greater than gravity. That's why you go up. However, at that force, your kinetic energy runs out and you end up being pushed back down. Now, you may well know, just to give you, to help you apply, this is simple, we're just going to work, but just to show you, you may well have seen this diagram before, alright? So I just want to kind of apply it to your physics for those of you that are doing it. Okay, so this is like this is a box on a table. Okay? Now, what we have is a centre of gravity. So gravity is applying a direction straight down. The slope it's on is applying a force perpendicular to its surface, and there is a force
Kinetic and
going this way.
Friction. So it's like
Friction
oh.
of the table.
We have paid attention.
but
Yeah.
don't you have to also gravity is it falling?
Well, is it falling is the question. Don't
Tilted.
but can you not put something on a slope
Yes, you
and not have it move?
It depends.
Because it doesn't have any.
If
I'm
it
doing
has
it.
friction.
If it has friction.
It's about to
Then you gotta
go.
have some grit.
That's
It's
friction.
like a box
Right.
of oil.
Now I just want to show you what we're talking about then. So, if I were to take these, I think I can do this. If I were to take these vectors, okay, this one, right? If I take that and then I apply, I think that there. So I'm adding my vectors together.
triangle.
Right. Well, actually, what's going to happen?
That's dirty.
It all links
So
together.
happy in my life. It's just a little bit too short.
Right now, yes. Now that's the thing. Now because there is a gap, all right,
Couldn't you make
it means that there's something else happening.
Oh.
All right. So because there is a gap in the magnitudes, now there is something else happening on this diagram, which
Maybe there's
No.
a small error.
so there'll be a force. Yeah. So I think.
What is it called when there's a leftover force?
So the resultant.
No.
No?
It's something else.
Now I think
Yeah, that's
I've just made up vectors, but obviously what would be happening if the gravitational force of the table pushing against, sorry, not gravitational force, and the frictional force, if they don't match up to the gravitational force, what's actually going to happen? We will have a going down the slope. Okay? Once you start going down the slope, then we can talk the energy that is being
Right now
accrued.
it's just all
Okay?
potential.
But just to show you, so that's your why are we adding and subtracting and things with vectors, because we have this kind of situation. Okay? Right, can I get you then? Can you do question 3?
Sure.
Just smirking.
I'm not smirking.
You're smirking.